Elon Musk says SpaceX will land on Mars by the end of 2026, 5 uncrewed Starships carrying Tesla's Optimus robots touching down on the red planet in about a year. NASA says 2035 at earliest. The physics says something entirely different. Here's why everyone's timeline is wrong and what the actual engineering challenges reveal about when humans will really reach Mars. In September 2024, Musk announced that the first Starships would launch to Mars during the November-December 2026 transfer window. If successful, crewed missions would follow in 2029 or 2031. By May 2025, he admitted there's only a 50-50 chance of hitting that target. The biggest obstacle? A technology SpaceX has never demonstrated, refueling a massive spacecraft in orbit using cryogenic propellants. This is the story of 3 competing timelines: Musk's optimism, NASA's caution, and what the physics actually demands. And why the gap between them reveals more about Mars than any single number ever could. SpaceX's Starship stands 120 meters tall. It's the most powerful rocket ever built, generating over 70 meganewtons of thrust at liftoff. To reach Mars, it needs something no spacecraft has ever achieved at this scale, transferring over 1,200 tons of cryogenic propellant between vehicles, while orbiting Earth at 28,000 kilometers per hour. That's the mission-critical technology. Not the rocket catching, not the heat shield, orbital refueling. Musk's own estimates say 8 tanker launches are needed to fully fuel one Mars-bound Starship. Each tanker launches to low Earth orbit, carrying roughly 150 tons of liquid oxygen and liquid methane. They dock with a propellant depot or directly with the Mars vehicle. The propellants transfer in microgravity, where liquids don't settle like they do on Earth. They form floating blobs that must be carefully managed using small thrusters to create artificial gravity. But there's a problem NASA's Government Accountability Office identified. Cryogenic propellants boil off. Liquid oxygen stays liquid at minus 183 degrees Celsius. Liquid methane at minus 162 degrees Celsius. In space, even with insulation, solar radiation heats the tanks. The propellants warm up, they evaporate, they're lost. NASA's analysis suggests 16 to 19 tanker flights per Mars mission, not 8. The difference? Boil-off losses during the weeks or months required to launch that many tankers in sequence. SpaceX would need to launch tankers in rapid succession to minimize losses. But even with 2 launch sites, Starbase in Texas and Launch Complex 39A in Florida, 19 launches in short order is unprecedented. In 2024, SpaceX transferred propellant between 2 internal tanks inside a single Starship during flight. That's the only orbital refueling test completed. Transferring propellant between 2 separate docked spacecraft is exponentially more complex. Temperature management becomes critical. When cryogenic liquid first contacts relatively warm transfer lines and empty tanks, some of it flash evaporates on contact. These are called parasitic losses. Nobody knows exactly how much propellant is lost this way because nobody's done it at this scale. There's another issue Musk disclosed in May 2025. Starship is experiencing a 50% performance shortfall. It's not delivering the payload capacity to orbit that was originally planned. If Starship can only lift 50 tons of propellant per tanker launch instead of 150 tons, suddenly you're not talking about 8 tanker flights or even 19. You're talking about 30 or more launches just to fuel one Mars vehicle. Former NASA Administrator Mike Griffin calculated the probability math. If each individual launch and refueling operation has a 98% success rate, which is optimistic for a brand new process, 5 tanker flights give you a 90% mission success probability. 20 launches, that drops to 67%. 30 launches, below 55%. That's the engineering reality behind Musk's 50-50 chance admission. Then there's the timeline Musk keeps revising. In 2016, he said SpaceX would land a modified Dragon capsule on Mars by 2018. In 2017, he said Starship would be ready in 5 years, meaning crewed Mars landings by 2024. In September 2024, he announced 2026 for uncrewed missions. By May 2025, he's calling it a coin flip. This pattern isn't unique to Mars. Musk promised full self-driving Tesla cars would be ready by 2017. Didn't happen. He promised the Tesla Semi in 2019. Delivered in limited numbers by 2022. He promised Starship's fifth test flight would include catching the booster in August 2024. It happened in October. Musk operates on what engineers call Elon time, aspirational deadlines that motivate teams but rarely align with physical reality. SpaceX has achieved remarkable things working this way. Falcon 9 is the most reliable rocket in history. Starship has made enormous progress in just 4 years of flight testing. But Mars isn't a software update you can patch later. The physics doesn't negotiate. NASA's official timeline says 2035 for crewed Mars missions. That date first appeared in the 2010 U.S. National Space Policy, targeting the 2030s. It's held relatively steady for 15 years, though internal NASA documents now suggest 2028 for Artemis 3, the moon landing that depends on Starship, has slipped because orbital refueling demonstrations won't happen until late 2026. If Starship can't reliably refuel in orbit by 2026, NASA's lunar program delays. If the lunar program delays, everything delays. The moon is NASA's proving ground for Mars. Technologies tested at Artemis Base Camp, life support systems, radiation shielding, in situ resource utilization, directly transfer to Mars mission planning. Artemis is the dress rehearsal. Mars is the opening night. So when NASA says 2035, they're not being conservative. They're calculating backwards from the Artemis timeline. Moon landing by 2028. Surface habitat by 2030. Lessons learned integrated into Mars architecture by 2032. First Mars mission hardware launches by 2033 to pre-position supplies. Crew launches 2035. But multiple planetary scientists now say 2035 is optimistic. They point to The Martian, the film set in 2035 showing humans already established on Mars. We're now 10 years past the film's 2015 release and 10 years from its fictional timeline. At this midpoint, robotic missions have advanced spectacularly. Perseverance is caching Mars samples for future return. Ingenuity proved helicopter flight works in Mars's thin atmosphere. We know more about Mars than ever, but we're not significantly closer to putting humans there. NASA's Mars Sample Return mission, just bringing rocks back to Earth, has ballooned to a $30 billion program with uncertain timelines. If returning a few kilograms of Martian soil costs that much, what does landing people cost? The physics creates the constraints. A Mars mission isn't one number, it's a delta V budget. Delta V measures the change in velocity a spacecraft needs to perform every maneuver. Earth to low Earth orbit, 9.4 kilometers per second. Low Earth orbit to Mars transfer, another 3.8 kilometers per second. Mars orbital insertion, 2.5 kilometers per second. Mars landing, 4.2 kilometers per second descent delta V. Then you have to come back. Total mission delta V for a Mars landing and return, 20 to 50 kilometers per second depending on mission architecture, gravity assists, and aerobraking capabilities. For comparison, Apollo missions to the moon required about 15 kilometers per second total. The rocket equation is exponential. Each additional kilometer per second of delta V requires exponentially more propellant. Small increases in energy requirements mean massive increases in vehicle size. This is why NASA spent decades developing the Space Launch System, a rocket that costs $4.1 billion per launch, while Starship aims to do it for $10 million per launch through full reusability. Reusability is the only way the economics work, but reusability requires orbital refueling, and orbital refueling is the technology that doesn't exist yet. Then there's the radiation problem. Mars missions take 6 to 9 months each way using conventional chemical propulsion. During that time, astronauts are exposed to galactic cosmic rays and solar particle events with no magnetic field protection. NASA research shows this radiation exposure increases cancer risk by approximately 5%. It also causes cognitive impairment. Studies on rats exposed to radiation similar to deep space conditions showed significant memory problems. Shorter transit times reduce radiation exposure. That's why Musk wants 80 to 150-day transfers instead of the standard 259-day home-on-transfer orbit. But faster transfers require more delta V, which requires more refueling, which brings you back to the same orbital refueling challenge. Nuclear thermal propulsion could cut transit time in half, but those systems are still developmental. NASA's nuclear thermal propulsion project aims for testing by 2027, but integration into Mars mission architecture is years beyond that. There's also the Mars landing itself. Mars's atmosphere is thick enough to require heat shields, but too thin for parachutes alone to work with heavy payloads. Every Mars rover has used a complex entry-descent-landing sequence. Starship would attempt a propulsive landing, firing engines to slow down, in an atmosphere that's 1% the density of Earth's. SpaceX hasn't tested this. Nobody has, not at Starship's mass. China adds another variable. The China National Space Administration announced plans for crewed Mars missions by 2033. Their timeline depends on the Long March 9 Super Heavy rocket being ready by 2030. China landed the Tianwen-1 rover on Mars in 2021, on their first attempt, something that took NASA multiple tries over decades. They built a space station in 2 years. Their lunar sample return mission worked flawlessly. China's space program operates differently than NASA. Centralized decision-making, long-term planning, less public scrutiny, less budget volatility. If they say 2033, they might actually hit 2033. That creates geopolitical pressure on NASA and SpaceX to move faster. But physics doesn't care about geopolitics. The question isn't whether humanity will reach Mars. The question is when the engineering reality catches up to the vision. Musk's 2026 timeline requires orbital refueling to work on the first try. It requires Starship to reach full payload capacity. It requires FAA approval for rapid launch cadence. It requires perfect execution of technologies that have never been demonstrated. That's the 50-50 chance he's talking about. Actually, it's generous. NASA's 2035 timeline requires Artemis to stay on schedule. It requires congressional funding to remain stable. It requires international partnerships to hold together. It requires technologies tested on the Moon to transfer directly to Mars. That's more realistic, but still optimistic. The physics timeline? That says 2040s. Maybe late 2030s if everything breaks right and multiple programs worldwide contribute. But more likely, 2040 to 2045 for the first human boot prints on Mars. The physics hasn't changed. The delta V requirements are the same. The radiation is still lethal over long durations. The orbital refueling challenge is still unsolved. Elon Musk's 2026 timeline requires miracles in engineering. NASA's 2035 timeline requires perfect political and technical execution. The actual physics says sometime in the 2040s, when the technologies have matured and the costs have dropped enough to make it sustainable. SpaceX will reach Mars. The question isn't if, but when. And the answer is not when Musk says.